So Europa is a massive googly eye, basically.
You're listening to The Cosmic Cast.
Hello, and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. I'm your co-host, Marissa Lowe, joined by John Pernay-Fisher.
Hello.
And Elliot Carter. And our wonderful guest this week is Mark Fox-Powell from the Open University.
Hi.
Hello, Mark. Thank you for joining us. How are you doing today?
Yeah, I'm really good, thanks. Got a cup of tea and the heating's on and it feels very cozy in here.
Can't go wrong.
Lovely.
So where are you joining us from today, Mark? Based on your background, you seem to be somewhere quite interesting.
Yeah, I'm actually in orbit around Jupiter's moon Europa.
Hence the need for a bit of warming cup of tea, I imagine.
Yeah, that's right. No, I'm just outside Milton Keynes in the southeast of England.
Fantastic, great. So yes, you study the icy worlds in our solar system. So can you tell us what's interesting about these moons, other than they look very, very cool, as we can see from your background?
Yes, well, they do look very, very cool, but there's more to it than that. So we've realized kind of in the last couple of decades, I guess, that several of them have subsurface oceans, so liquid water layers deep under the surface where at least a few of them, there may be potential for water rock interaction. And where we see that happening on Earth, we tend to see life. So we think that there's a good reason to believe that some of these moons, like Europa behind me, might be habitable for kind of simple organisms or potentially, just any kind of life, really. So that's made them a kind of priority for solar system exploration, and there's lots to understand.
Mm-hmm. So you said they have these subsurface oceans. Mm-hmm. What is the structure of these different moons like?
So it kind of depends on size. So there's quite a large range of size of these, what they call them, the ocean worlds. So we go from Enceladus, which is a moon of Saturn, and it's only about 500 kilometers in diameter, up to Titan and Ganymede. So Titan is a moon of Saturn, and Ganymede is a moon of Jupiter. And these things are planet size. I mean, they're larger than Mercury. And so the size matters because this affects the kind of the interior structure. So they all have silicate cores, and then a large amount of water. And the water is differentiated into liquid and solid ice. But other larger moons, you actually have these high pressure ice phases, which can form really basically at the core ocean boundary. So places like Titan and Ganymede, possibly Callisto as well, another moon of Jupiter, you can have these high pressure ice phases, which maybe limits the potential for water rock interaction. So that actually has relevance for astrobiology and potential for life.
Yeah.
Is it a coincidence that they're all moons around these big planets?
Well, I guess the main point there is a distance from the sun. So you condense the volatile. There's a lot more volatiles. You have a lot higher sort of water to silicate ratio at that distance from the sun, just accreted. But in terms of, would you find something like this orbiting the sun freely? I don't know. I've never actually thought about that. I suppose maybe.
I guess they all sort of fall past the snow line, isn't it? Which I guess is
that's right.
Hypothetical line. Where is it exactly? In the asteroid belt somewhere, maybe? I'm not actually sure.
A little bit, sort of outer edge of the asteroid belt. It's closer in than Jupiter, anyway.
Yeah. So how exactly do you study these planets? Obviously, they're far away, and I guess there's only been a handful of missions to some of these icy worlds. Do you mostly use some of this data? Are you mostly an experimental person, or what's your angle on this?
Yeah, so my angle is entirely sort of contextual science for the missions. I don't do any observations myself, at least not yet. So I'm doing lab experiments, primarily, sort of. So far in my career, it's been lab experiments and a bit of field work as well, actually.
Really? Cool.
That sounds a little bit surprising, given that we don't really have much like this on Earth. But depending on the process you're interested in, you actually can find some interesting analogs on the Earth. But so I do lab experiments to try and explain some of the observational data or try and understand a bit more what it's telling us. But you're absolutely right. We've got, we've had there's a big imbalance between some of these moons as well. So Enceladus is probably the best understood in terms of the ocean, just because the Cassini spacecraft was in operation until 2017 and managed to do many flybys of Enceladus, where it was actually able to kind of go hands-on and capture particles that were ejected in the really active southern polar plumes of Enceladus. And they, we think, come directly from the ocean. So that there's kind of a sampling of the ocean that's happened there, which you cannot say the same for any of the Jovian moons, the Galilean moons of Jupiter, which we rely on the Galileo mission, which was in the 90s. And sort of there's a new generation now of Earth-based telescope observations of Europa and Ganymede, which are sort of laying the groundwork for a new generation of missions.
Do you find that sort of lack of data quite frustrating sometimes when you sort of see other people in their huge Martian and lunar data sets?
I don't think I find it frustrating. I think some people, I think the pure fact that I'm working on it means that I'm quite happy with the, like I would love to know more about it, but there's something about the kind of the wide open questions and the huge unknowns that I find quite tantalizing for some reason. I think I've spoken to people who, you have this people who study Mars can't get their heads around, like how little there is to go on with some of these moons. But then people who are terrestrial geoscientists, like Elliot, I guess, will look at Mars and think, how did you guys conclude anything? Because we've barely got any. We've got like 7 landed missions on the surface of Mars. Imagine if all we knew about the Earth came from 7 locations on the surface.
A bunch of random rocks from where they're from.
So yeah, I completely sympathise with that point of view.
Yeah, that's giving me cold sweats.
But I'm quite happy with the something about the wide open questions I find really, really interesting. Having said that, I can't wait for the new missions. So.
Well, I guess that leads quite nicely into how can we use fieldwork on Earth to make links to these faraway worlds?
So, well, a range of ways, I guess. What I've done with the field stuff, there's a kind of couple ways that analogs can be useful, I guess. One of them is just understanding a fundamental process. So let's say we have a little bit of information from somewhere like Europa, and we think that, oh, okay, this feature on the surface might have formed through a process which we can find an analogy for on Earth. So we go to that place on Earth and then learn a bit more about that type of process, how it functions on Earth, and then kind of try and extrapolate what we can. But there's also, the real value of an analog on Earth is just to kind of go through the motions of mission relevant data collection. So use kind of relevant sample material for characterizing, for looking at kind of instrument development and stuff like this under realistic, sort of geochemically realistic samples. So I've done a bit of both of those things, I guess. And what I tend to be focusing on is the surface material on these moons. So behind me, you can see the kind of weird, crazy, chaotic features you see on the surface of Europa, a lot of which we think result from tectonic type activity. It's not really tectonics in the way that it happens on Earth, but it's similar. And associated with that is material that we think has come up from the ocean and just kind of been emplaced on the surface. So using the composition of that material, you can kind of get some idea about the composition of the ocean. And pretty much all of my work nowadays is centered around understanding that link. So understanding those processes. Mm-hmm. So what I do in terms of field work is try and find locations where either where you have solute-rich fluids, aqueous fluids, freezing and depositing their dissolved components. So these are like salts and things like that, and will form as you freeze the fluid. So this could be sea ice, but it could also be, there's various other places in the world on Earth where you get that process happening. Lake covers and there's glacial springs, things like this that freeze in winter, and we can go and sample them and look at kind of how the composition changes. And then also just anywhere in the polar regions or the cold regions where you have salts forming that are low temperature phases. So these hydrated salts, they're salts that have water molecules sort of stuck into their structure, and they don't have to always form in ice. They often do. So sea ice will have loads of these things in them, but you can also form them just on the surface through evaporation. And but normally when you get kind of salts forming, you find them in deserts and hot places. But I'm kind of trying to seek out those areas in the kind of colder regions of the Earth where you get these low temperature salt phases forming, and they're similar to what we think we see on the surface of the moon, like Europa.
And
so
I guess
is this basically like igneous petrology, but for ice, for like water instead of lava? Yeah,
it's kind of funny you say that, because I before coming to the OU, I was a postdoc in St Andrews, and it's a geochemistry and sort of geology heavy department, which is not my background actually. We can go into that in a minute if you want. How I've ended up in this, but there, kind of talking to the geologists, I mean, you kind of realize like, oh, this is igneous petrology. It's just in a different temperature regime.
Yeah, that's so interesting.
I do really like thinking about it in those ways. And is that a thin section picture behind you, Elliot?
Yeah, it's a bunch of olivines.
Okay, so I'm kind of developing some protocols to do similar stuff with sort of experimental what we call cryomagmas or cryolavas, which are basically just frozen brines, right? Yeah. So I've done a bit already using cryo SEM systems, but it was a bit, so it was very much a kind of let's see what the potential is with this approach. But now I think there's scope to kind of really get really quantitative with it and look at element partitioning and things like that. It could be quite fun.
That's really cool. So I guess then thinking about then these sort of trace elements and even some of these mineral, well, I guess they are, these sort of salty mineral phases then, ultimately, are they telling you about what's going on in the silicate portion? Because presumably all these salts and stuff are a function of that basal water crust interaction, or?
Yeah, they ultimately, you're right. I mean, what you're seeing on the surface is the result of a kind of core to surface process. It's the very end point of that. Most of the non-water ice stuff you see on the surface, there are some important caveats to this actually, which I'll come back to, but most of what you see on the surface that's not water ice has originated in the silicates, right? And kind of been weathered out, or, through alteration has just kind of ended up in the ocean. So you could use it as a way of investigating the silicates, but I don't usually make that mental leap. I'm more interested in the ocean chemistry itself. Yeah. And then I can, I collaborate with people who think more about the silicate portion to make that link, but that's certainly not my area, really. I think more about the ocean and how the ocean relates to the surface.
It's so similar to igneous geochemistry. It's really funny because that's the same as how we probe the mantle, really. Most of what we understand about the mantle is through mid-ocean ridge basalts.
There are some important differences in the sense when you get into the geophysics of it, but I mean, the oceans here on these moons are kind of like a mantle, and the icy, you even have the icy shell termed a lithosphere. People do call it that because it kind of behaves like one. There's important differences in the sense that ice as a solid is way less dense than liquid, so that's why the tectonics are all a bit weird. It's hard to subduct stuff and things like this because of the buoyancy issues. But
because you used the terms like cryolavas before, and I'm sure lots of people have heard the term like cryovolcanism. How does that work? Because we imagine here some sort of magma on Earth, some sort of magma chamber, something triggers that and makes that ascend. It'll erupt onto the surface in a number of different ways. What is cryovolcanism like then?
Well, it's important probably to say that that it's not very well understood. It certainly is happening because we can see very dramatically at a moon like Enceladus. I don't know if people have actually seen. Surely most people watching this will be familiar with Enceladus, but it has these really huge plumes of water ice essentially coming out of the South Pole. Water ice vapor, some gases coming out of the South Pole. So this is a really obvious illustration of cryovolcanism. It's definitely happening.
Yeah.
But
So
the
we had Rachel Hamp talk about this a few weeks ago, didn't we? And we'll put a link to it as a little eye or something in the top corner of the video over there, I guess, somewhere on the corner of the screen. There'll be a link to that video.
Yeah. Yeah. So it's definitely happening. But the mechanisms that drive it are not that well understood. So there's various different sort of proposed mechanisms, and you can have at Enceladus. We think essentially that at some depth in these kind of cracks in the icy shell, that the ocean is effectively open to vacuum, and it's essentially just boiling off, and that's what's driving it. You could have other situations where you have a melt lens in the shallow subsurface, which is kind of like a magma chamber. You know, how that forms in the first place that's another question. But let's say you do have one, so a melt has formed in the subsurface. As that refreezes, just the pressurization from the ice forming in situ can force the remaining liquid upwards and deform the surface. And actually, that model matches really nicely with some of the features that are seen on Europa's surface. Like maybe that one there, in fact. Don't quote me on that. If there's any Europa geology experts watching this, I'm not sure if it's one of those features, but it looks a little bit like one.
Are there any other moons where they've observed cryovolcanism?
Well, so active cryovolcanism, there is some evidence that it's happening at Europa. There have been maybe some plumes detected there. I say maybe because I think it's a little bit debated, but it certainly seems like it's very likely that this is happening at Europa, at least transiently. But also Neptune's moon Triton has been observed to have active cryovolcanism, whether that is water cryovolcanism, or it actually could be nitrogen cryovolcanism.
Oh wow, so that's even colder then.
Even colder, yeah. It's a lot of nitrogen on Triton. So
that's insane.
Yeah.
So what's driving a lot of this then? I mean, if it's just a sort of a silicate core and there's no proper mantle, or is it radioactive elements in the silicate portion that's driving heat, or is it just like a pressure thing, or?
I think most of the heat is thought to come from a combination of radioactive decay and tidal deformation.
Oh, yes, of course, yes, tidal, yeah.
Yeah, so the Galilean moons of Jupiter are all in resonance of some kind. I can't remember the numbers now, but so they're all interacting in a way that generates a lot of tidal energy. And you can actually see when you look at them, the closest one to Jupiter is Io, which of course is, if it ever had lots of water, it's long gone, and it's extremely volcanically active. And then you have Europa as the next one, and it's covered in stuff like this. And then the next one out is Ganymede, which still has a bit of this kind of stuff, but it's a bit more heavily cratered. So it's an older surface, less resurfaced. And then Callisto is the furthest one out, and actually is a very old surface, heavily cratered. So you can kind of see the effects of that tidal heating decreasing with distance. Cool. I think at Saturn, similar things happen, but there's a bit of a question mark over Enceladus. Enceladus seems to have too much heat then can be explained through these two processes, radioactive decay and tidal. So something else is going on there. There's a piece of the puzzle missing.
Yeah. That's amazing. So do we have a handle on how cold these things are then at like the surface or in the near surface? Because presumably all the different salts in there are going to be changing the sort of traditional boiling points and all that kind of stuff. Must be just thinking about how because I guess like if you're thinking about cryovolcanism, the thing that occurred to me is like phase equilibria. It'd be quite cool to sort of trace out all the different mineral phases that should be present at various PT conditions, but I guess that must be quite a difficult thing to do. So that might just be me, however.
John, I think you have a larger than average soft spot for phase equilibrium diagrams.
I was actually sort of doing that this morning.
Oh really? Oh, there we go.
Yeah. So I mean, yes, kind of. We don't. So there's very little experimental data on a lot of these phases under the relevant conditions, especially when it comes to pressure. Right, people haven't done the experiments really. There are very few places in the world to do high pressure, low temperature experiments. Where you're talking about below 0 C and high pressure.
Yeah. Can't just
but
put
then
one of
again-
those anvils in the freezer or something.
Yeah,
Yeah.
well,
I mean, geology low temperature is anything up to 200 degrees. Like that's
Yeah,
low
yeah.
temperature.
yeah,
It's not -50. Like that's zero as far as geologists are concerned, right?
yeah, for sure. But the thing is, so the pressure regime that we're talking about actually is not very high. So we tend to just, in the work that I do, I do think a lot about, mineral phases precipitating at different temperatures within the icy shell, things like that. We tend to just discount pressure at this point because, Europa, you have about, well, it's debated, but maybe 10 up to 30 kilometers of ice. But obviously, Europa is much less massive than the Earth, so that the pressure at the base of the ice shell is not actually that high. I was about to say a number. I'd have to look it up. So maybe if you want me to look like I know that, maybe you want to edit this bit out. But I don't know that.
We just hear lots of tapping and clicking.
I do know. I'm pretty sure that the pressure at the bottom of the ocean. So we're talking now under about 100 kilometers of water split into liquid and ice, is similar to the pressure at the bottom of Earth's oceans. So we're not talking crazy high pressures.
Yeah.
But the temperature obviously is interesting because we usually assume that we go from about 0 C at the base of the ice shell to the surface temperature, which at Europa is about 100 Kelvin, so like minus 170 C. And Enceladus, it's even colder, so maybe 70 Kelvin. So it's that gradient of temperature that is kind of where all the stuff that I think about happens, I guess.
This might be quite a basic question, but how do we actually know there's an ocean there? Like, how was that originally discovered?
So it's to do with there's a number of kind of different lines of evidence that have all kind of stacked up. One of the main ones is like an induced magnetic field. So Jupiter has a big magnetic field, so does Saturn, and the way that these moons interact with it basically can only be explained if you have a conducting layer, which is best explained by a salty liquid layer, liquid water layer. But then, then they've kind of, from there's been, a lot of these features here are very hard to explain without some kind of geological activity. Europa's got very low amount of craters, so it's resurfaced. In fact, the average surface age is something like 100 million years.
Wow. Very
young surface. So there's a bunch of different lines of evidence, but the primary kind of geophysics line of evidence, I think, is this induced magnetic field.
I realised we were.
Sorry.
No, go on.
The icy shell is decoupled from the interior, so that the way the thing is moving is not explained by the inertia of the satellite.
That's so cool.
Yeah.
That's madness to think of that.
So
to think of that on that scale.
Yeah.
Like, I don't know if any of you had those like toys when you were younger, when it was like one ball inside the other.
Yeah, with the
and you
the
could
eye.
try and move the inside one without moving while moving the outside. I don't know. I'm just picturing that now.
I know what you mean. Yeah.
Yeah, that's exactly what I was picturing. That's so cool.
Yeah, it's mad.
So Europa is a massive googly eye, basically.
If we've learned nothing else today.
That's amazing. So how come you? So have you mostly in the research that you've done? Is that mostly been on Europa, or have there been other moons as well?
So I'm a bit of a weird mixed bag. I did my PhD was actually focused on Mars.
Oh, okay.
And so I moved into the icy moons during my postdoc, and that was kind of a conscious decision, just out of interest, but also kind of realizing that there's these new missions coming up in the 2020s, and at conferences I wasn't speaking to many people in the UK who were working on icy moons, so I thought I might just do that. But I was working on similar processes on Mars. I was thinking a lot about brines and salt formation, brines that are stable against low temperatures, things like this, and their habitability for microorganisms at the time. So there is kind of a logical thread that led me here. But my work on my postdoc and currently is basically focused around two moons. It's Enceladus, because we have, as I was saying earlier, kind of the best constraints on the ocean from the Cassini mission. And so it allows us to do a bit more than we might do at Europa in terms of understanding processes. But then also Europa, and the reason Europa is so interesting, it's the one out of all the Galilean moons, it's the one that doesn't have, at least as far as we know, these high pressure ice phases. So we probably have ocean core interaction going on there, and also it's the target of a couple of upcoming missions. There's one from the European Space Agency and one from NASA. Ganymede is also super interesting. Don't get me wrong. I think Ganymede is the kind of, no one talks about Ganymede.
Like the dark horse.
Yeah, it's a dark horse, exactly. I think there's going to be a lot of interesting things to find when we get to Ganymede. JUICE, the European Space Agency mission, is going into orbit around Ganymede. Okay. So that's going to be pretty cool. I
guess so. Is Ganymede just not being focused so much because it's relatively much fewer data out there on?
Yeah, I mean, Ganymede has its kind of fans. People wave the Ganymede flag, but I think I'm talking about in terms of astrobiology. So people thinking about the potential for life, it tends not to get considered so much just because of this high pressure ice part of the story. But I don't think that there's reason to believe that's not as effective a seal for water rock interaction than people think.
So you were just saying then, I think you touched on the astrobiological reasons for doing this research at the start of the episode. A question that we ask a lot of people when they're searching for life on other bodies in the solar system is, what does that life look like? What would it look like if you were going to have a nice eureka moment where you suddenly found evidence of life or life itself? What would it look like?
I actually have tried to imagine this quite a lot at Europa, somewhere like Europa, one of these ocean worlds.
Fish, it's got to be fish, surely.
Well, okay, well, some people actually think that okay, so a couple of things. So first of all, you can get, I'm looking behind me as if I will actually see that picture there, but of course it's not. So Europa is in a high radiation environment, and you can get lots of hydrolysis of water. So water being split apart by water molecules being split apart by radiation. That creates oxidants that, if the surface is being resurfaced roughly every 100 million years, that can get delivered to the ocean. And some people think that, some people have done some calculations to speculate that you could get enough oxidants into the ocean to support big animals like whales and stuff. I mean, that's like at the one end of the one end of the scale, the kind of upper limit. I mean, that's, who knows? We have no constraints on how
Wales
much.
on Europa confirmed.
Yeah.
There we go.
Yeah, Wales on Europa confirmed. Yeah, that's right. But no, I tend to think about the fact that you might have deep sea hydrothermal input into the ocean, and life will kind of cluster around the chemical gradients like it does on Earth, and you might even have, because you can have maybe even 100 kilometers of ocean depth, these gradients could be spread out over huge distances, so you could have these massive sort of microbial biofilms that kind of like chimneys almost rising up into the ocean. That's kind of what I picture, exploiting kind of plume gradient from the hydrothermal system.
I guess we've touched on this before in previous episodes, but I suppose this comes back to this idea that that similar processes, these so-called black smokers, are still, I guess, one of the main theories for how life started on Earth, aren't they? So I guess if it happened on Earth, why not on other icy bodies, I guess?
Yeah, I mean, that means that it's a question worth answering for sure. If it didn't happen there, then why not? What's different about the Earth?
Yeah, that's really cool. So just to put you on the spot then, Europa or Enceladus, where are we going to find life?
I mean, okay, I'm very agnostic about whether life exists in the solar system. I wouldn't put money on it. But I think out of the two, probably if I had to bet, I would bet on Europa. We know less about it right now, so that might change. but it's just it's just a larger kind of more dynamic, more complex world. I feel, and also Enceladus may have not been active for that long. We don't really know how long Enceladus has been doing what it's doing right now.
Is it an older surface then, I guess?
It's an older surface. Also, there's speculation that the Saturn system in its current state is maybe not that old, depending on how old the ring system is. It could the rings system could be the remnants of an old moon. If that's broken up, then who knows what else has happened in the Saturn system. Whereas there's reason to believe that Jupiter's system has been stable for a long time. So so just based on time, what I'm talking about here is obviously not consensus, but in terms of Saturn, but the Jupiter system could have been stable. Europa could have been doing its thing for 4.5 billion years. So
interesting.
Don't worry, we won't be titling the episode, Europa versus. Yeah, it won't be a brawl match or anything.
Yeah. Well, it's interesting that you use the word agnostic, though. I guess we ask a lot of people, how optimistic do you think that we will find that life in other parts of the solar system? Then, would you put yourself in the optimistic camp, or would you rather not pass comment until we see harder data?
Honestly, I'm firmly on the fence.
Okay.
I can convince myself either way, right? So you can convince yourself that, surely we have. Anywhere where we have the right kind of conditions and the right kind of chemistry, surely we must have it. And then on the other hand, I can convince myself that the Earth is quite unique, and we just have no idea really what led, or what no idea, but we don't have a good handle on what led to the origin of life. So I don't like to say either way. I think either answer is super interesting.
Yeah, no, for sure.
Tells us something pretty amazing about how life begins and our kind of
place.
Sounds cheesy, but like our place in the.
And I mean, along the way, you get some pretty beautiful images of these different icy bodies, and also get to visit some pretty cool places. So yeah, I wanted to ask, where's your favorite analog site been that you visited?
Well, it's got to be the Canadian High Arctic. So as part of my postdoc in 2017, we went to Axel Heiberg Island, which is as part of the Canadian Arctic islands, archipelago. And it's just an incredible place. I mean, it's uninhabited. It's just full of muskox and wolves and stuff. And
wow.
It's just an incredible, beautiful part of the world. I mean, I feel really privileged to have managed to go there. The reason we went there is it has this series of these salt springs, which are cold. They're below 0 C all year round, actually. So they're buffered to that temperature by a high level of dissolved salt, so they don't freeze. And also there's 400 meters of permafrost. So they're kind of kept at this temperature. And these things deposit a load of these hydrated salt compounds, similar to the things we think exist on the surface of Europa.
Is that what gives the sort of discoloration that we see on Europa there, these salt compounds?
That's actually something that's, again, kind of been a bit debated. I think this is a false color image, or at least it's an exaggerated image. But they do have a reddish tint. They do have absorptions in the visible part of the spectrum where red is. And I think people have suggested that it could be tholins, which are these kind of radioactivity generated organic compounds that we see on moons like Titan. But I think that's there's not enough organic chemistry going on to really explain that. The really interesting one that seems to be gaining traction at the moment is if you take table salt, just literally salt from your cupboard, sodium chloride, it's the same stuff that's dissolved in Earth's oceans, lots of it. And as the salt, if you shoot radiation at it, high energy electrons, it'll go that color.
Okay, interesting.
So something for the listeners to try at home.
You've got access to an electron gun. then
yeah, does everyone.
Take apart the old telly.
Yeah. But yeah, so they turn a kind of brownish color, and this is one of the really frustrating things about the lack of data, is that that's actually a really simple thing to try and test observationally, right? Oh, we see this color develop if we do the lab experiments, and we can measure the spectrum of that, but we don't actually have that. The data from that part of the spectrum is missing from the Galileo data sets. There's just a gap. so there's no data from Galileo. We do have data from ground-based telescopes, but of course they don't have the spatial resolution to be able to tell the difference between that bit and that bit and this bit.
Yeah.
They just see the whole disk essentially. But there's evidence building that that's what drives this red color. Yeah. Anyway.
Yeah. Oh, sorry, we went on a tangent. You were talking about your
yeah. Yeah, I was talking about Axel Heiberg. Yeah, that's right. Yeah, beautiful place. Forms these hydrated salt minerals. And there's very few places in the world that do that. So it was worth the visit.
So what exactly did you do? Take samples of these salts or study?
Yeah. So basically just sampled the hell out of it. Yeah. So we visited 3 springs. They're really different chemically. Their compositions are very different. It's funny because you look at the major composition of the brines, they're all very similar, but minor differences in certain ion ratios mean you have these really different salt deposits, which is a good lesson for looking at other planetary bodies and reconstructing fluid compositions from minerals, which is what a lot of people do. Do it on Mars, we do it on Ceres, we do it on the icy moons. So we were trying to understand the relationship between the salt deposits and the brine in terms of its chemistry, but also we were looking at microbiology. I've got collaborators who are doing microbiology work on these springs, including some of my colleagues here at the OU and at St Andrews. We've been working with a team at NASA Goddard looking at using mission relevant techniques on the salts to kind of look at whether we can see organics that are trapped in these salts, things like that. What else? We've done a bit of sulfur isotope geochemistry to try and look for if we have evidence of biological activity that's happening in the brine being deposited in the salts that we can then measure with the sulfur isotopes. There's a whole load of stuff going on off the back of these samples, basically. And thing is, it's such a remote and difficult place to access that once you get samples, you just kind of want to do everything with them, maximize the return.
And I guess because they're so difficult to get to, they've not been studied particularly well up to this point, I suppose, or...
So they've been studied a bit from the point of view of their hydrology, so how they form, why they're there in the first place, and have been a little bit of microbiology work done on them as well. But this is certainly the first sort of planetary focused research that's
really cool.
analog stuff that's come out of it.
Do you have to keep them cold, or can you just put them in a vial, take them away, or whatever?
Yeah, good question. I mean, they have to stay cold. Yeah, so that makes everything challenging. Everything that I do essentially nowadays involves some challenge keeping things cold. Luckily, with these salts, they're not ice, so you don't need to keep them sub-zero. But the major salts there are things like mirabolite, which is a sodium sulfate 10H2O, and it will dehydrate at about 15 degrees, 10 degrees, some in that range. So room temperature, it's a puddle. So yeah, you got to keep them cold. So it was okay when we were up there because it's cold there. So we just kind of stored them outside in the sample box, outside the tent. But then shipping them back, I mean, you just have to hope that your trip doesn't last too long, basically. I took them as hold luggage on the plane.
Really?
Yeah.
Oh wow. Okay. So when you say you don't want it to last too long, you really mean quick dash?
Yeah, we weren't. So we could have shipped them, which is obviously possible, refrigerated, and would have been very expensive, but possible. But we decided to not do that because we'd spent a lot of money getting there in the first place.
Yeah.
So we just decided I was just going to basically courier them myself by taking them on the plane. And it was kind of funny because at the airport in Ottawa, flying back from Canada, I think the weight. So I had them in a big like insulated box, packed full of ice packs and stuff, and it was like an 8-hour flight or something home, and that was going to be fine. I knew that they would hold their temperature for 8 hours. There's no worries. But at the check-in, they measured the weight and they were like, "Oh, it's half a kilo over the maximum weight, so you have to now ship it as freight, and it'll take a week."
No.
So I basically was like trying to argue my case, and the person behind the desk was really on my side, and it was quite funny. I had my name and address like printed and stuck on the box, and it said like Dr. Mark Fox-Powell or whatever. And she was on the phone talking to the baggage handlers, saying things like, "We've got a doctor here with samples from the Arctic. You need to get on that plane." It was hilarious.
Excellent.
Amazing. That's such a nice sci-fi movie moment there.
Yeah.
That's really
I'm not that kind of doctor, but I'm not gonna argue.
full of Martin Morgans. So how did you get up there then? Did you charter a flight, or is it sort of a boat trip up to these sort of islands?
You charter a flight, kind of. It's supported by the Canadian government. They have like essentially, is it the government? It's a body. It's a organization in Canada that's a bit like British Antarctic Survey, I guess. That basically do all the logistics for Arctic, high Arctic field work.
Yeah.
So you have to apply to them, and they basically support. If they like your project, like proposal, they will support your trip.
Okay. That's good.
So yeah, but you fly up in a twin otter, like one of those. You might have seen pictures of those things.
Yeah, well, I guess it's what they use down in Antarctica as well, isn't it?
Yeah, exactly. It's actually the same crew, like the same pilots.
Oh, really?
Yeah, they literally spend the northern summers flying in the Arctic, and then the southern summers in Antarctica. It's the same aircraft. They hop them all the way down the coast of the Americas.
Really?
Over the course of about 2 or 3 weeks. Yeah.
That's amazing.
Wow.
Wow, what a journey that must be.
Yeah. Yeah.
Oh,
Cool.
That's a serious road trip.
Yeah.
Not a road trip, but
Just anything to avoid the summer.
yeah.
That's really cool. That's amazing. I have no idea.
Yeah. Yeah. So, Mark, how did you end up studying icy moons and getting to go to such spectacular places all over Earth?
I have a really weird sort of patchwork career so far, history. So my undergrad was actually in marine biology at the University of Plymouth, and from there, then that was really essentially like an ecology, an evolution focused program. It's a real kind of biology program. But I did a master's there in marine microbiology, where I was looking at viruses, marine viruses.
Okay.
And I always had this kind of fascination with the big questions of, does life exist beyond Earth? How common is life in the universe? But I didn't realize that was like a field, particularly like an actual a focus of research. And it was when I was looking for PhDs that I saw one being advertised that was like an astrobiology PhD. And it was actually said a PhD in astrobiology. And I have to apply for this, absolutely have to apply. So taking my kind of microbiology background, I went into this PhD, which had quite a significant geochemistry component. And as like a first year PhD student, suddenly you're reading literature about Martian geochemistry and stuff. And I was like, oh my God, I cannot make head or tail of this. So it's like a really steep learning curve, but going through that now has made me really enjoy these like interdisciplinary projects and ways of thinking and stuff. And I've ended up following the geochemistry side of things more and more over the last few years. So the step from Mars to icy moons was just kind of, it made logical sense at the time. And my boss in St. Andrews, Claire Cousins, we had this grant that was accepted from Leverhulme that funded this icy moons project, and I was there and I was ready to do it. So it seemed like the logical step. the types of processes I was working on my PhD, brines on Mars, translated well into the icy moons sort of setting. And yeah, I guess I haven't really looked back from there. I'm still involved in biology, so I collaborate on biology projects. I think about habitability quite a lot, and I have that kind of background, but yeah, I've sort of gradually migrated away from what I originally started as.
But then again, if there are whales in the waters of these icy moons, you've actually come full circle. So that you're just one discovery away, and that's just come back round. Amazing.
I did my undergrad dissertation project on sea anemones, so maybe one day I'll be studying sea anemones on Europa.
Absolutely.
Exactly. Yes.
Yeah.
Amazing. Wow.
Space anemones, surely.
It's anemones, actually, isn't it?
Oh, is it?
Anemones.
Anemone.
One of those words.
Yeah, that's one of those where I can convince myself either way.
I'm just going to be saying space whales to myself all day now.
Well, I've learned so much during this episode. Thank you, Mark.
Yeah, really interesting.
Yeah, it sounds like you do so much amazing stuff. So yeah, thank you for coming on. We do have one final question for you. And yeah, you said you've listened to the podcast before, so you might already know what it is, but if you could be doing something else in academia or outside of academia, what would you want to do?
Oh, wow. I wasn't actually prepared for that. It's funny, like I think about this weirdly quite often, but I always have a different answer. But I've always loved just like manual, hands-on tasks. And that's when I'm happiest in science as well. It's like either in the lab or in the field, particularly in the field, outdoors, getting my hands dirty. I'm always super happy to wake up really early and start working and work hard all day when I'm on field work. You know, there's something about that. So any job that has me outdoors would be kind of the best. A friend of mine works on a salmon farm up in the north of Scotland. So that's always been on the back of my mind as a kind of like potential sort of alternate career. Just kind of go out there and farm salmon.
Yeah,
you know?
fair enough.
Sounds lovely, yeah. Yeah,
I know
an
icy planet with a nice ocean. Salmon farm on Europa.
Salmon farm on Europa, there we go, yeah. Delicious European salmon.
Oh, amazing. Well, thanks again, Mark. It's been a real pleasure to chat to you.
Yeah, well, thanks, guys.
Yeah, wonderful.
I really enjoyed it as well. It was really good fun.
That's great to hear.
No
But yes, for all the listeners at home, thank you very much for listening. And if you'd like any more Earth and planetary science content, all of the links will be in the description. Thank you, John. Description. Amazing. Thank you very much, everyone, and goodbye.
Bye.